Thank you, Josh. My name is Thomas LeBlanc. We're talking about execution plans in SQL Server today. I think I'm a data warehouse architect, but some people think otherwise. I've been an MVP, luckily or fortunately, in the data platform for the past 4 years. I consider myself a data warehouse or a business intelligence architect, but I still do DBA work, like looking at execution plans. In the beginning of working with data, when I became a database administrator, people used to call me a database normalization nut. And your structure, relational structure, wasn't in third, fourth, or fifth normal form, you kind of got the wrath of Thomas on you. The thing was, is the developers never listened to me anyway. So I moved on to data warehousing, where you can do whatever you want. So I like to say I'm crazy about dimensional modeling today. And in the past, I was a developer, but I retired out of that and no longer developed software. I did VB through 4 or 5 versions, FoxPro, Visual FoxPro, and in college I was doing COBOL programming. On the Twitter, Gmail, or blog, you can find me, the Smiling DBA. And my nickname I created on Twitter a while back. Told me not to change it. I do volunteer for a lot of things. A lot of it in the past was with the Professional Association of SQL Server. I was a chair of some of the virtual chapters, the nomination committee. I'm still involved with our local SQL Server user group and analytics user group. We kind of merged them all into something called the Baton Rouge user groups. And we're actually putting on a SQL Saturday, August 6th. Myself and about 4 or 5 other people got together and decided to light that back up, and got a good response from the community and local people. So we're really excited about having another in-person event after 2 years. Assumptions about you I'm making is that you can write T-SQL. You had limited or not really used execution plans or query plans, whatever you want to call them. You could be a developer, a DBA, or just some cool IDD. And hopefully you have a little sense of humor along the way. What we're going to talk about today is some terminology that was used with execution plans. We'll look at the history of execution plans, kind of to show you that Microsoft is always improving what we're able to use, even though sometimes you get some minor irritations with some things. We'll have plenty of demos. This whole session should be about demos. And we'll even talk about some new features. There were new features like in 2017 and 2019. I guess today, I think they've done a public preview of 2022. So I haven't even seen what's new in execution plans from the Build conference today. History, back in the day, before you had SQL Server Management Studio or Azure Data Studio, you had something called Enterprise Manager, and really the execution plan was a piece of text that you looked at. And we'll look at that. We can actually go see that still today. In 2005, you got these graphical plans. 2008, missing index. There were other additions. I'm just highlighting some. A big deal in 2012 was these warnings about memory grant. The operator cost was added, and I thought was a big deal. Was the query store, especially when you were able to compare plans. And I really like the live query statistics that came between 2016 SP2 and 2017. In 2017, they improved the query store. Somewhere between 2017 and 19, they had something called adaptive query joins, which we'll see an example of that. And SQL Server Management Studio continuously has new things, and the analyze actual query plan was kind of a cool one. So you kind of see the history and realize how long I've been using SQL Server. But we'll go ahead and shoot for the demos. All right, so got a little set of queries here. The first one, I'm just going to make sure my database is kind of cleaned out of any indexes I had from my previous demonstration. And we're gonna look at the text query plan. So I'm gonna go in the database, I'm gonna set the show plan underscore text on, and then I can run a query. And the output is actually the query and the text, but I can't really see it well there because it's in a grid, but there's a way to change that in Management Studio where you say results to text. And run it again, and now we actually have the results in a text. And here is our query plan. It's pretty much a table scan, looking down here. It's a table scan on a particular object database log. So obviously the table does not have a clustered index on it, and you just have really one level. It's just execute query plan. execute the table scan. So here I'm gonna do a little bit more with the query, and then you'll see a set of indented kind of iterators is what you would call them in the execution plan today. And you kind of read them from inside up like that. So, the first thing we have is this clustered index scan. We get 2 compute scalars, and then we have a filter, which is our where clause. The compute scalar is because the table has a calculated column called total due, which is doing this addition that we see in the previous row. So that's how you actually had to read the query plan or the execution plan back in the day. It was a piece of text. That's how you figured things out. Of course, Microsoft, has improved on that. I'm gonna set that off, put my results back to grid, and then just display I'm sorry, I wanted to just display estimated execution plan. So I'm gonna select my text, display the plan. A neat thing someone showed me not too long ago at a talk I did is like, hey, you can zoom to fit, and never knew that. I was always zooming in and out, and there was a zoom to fit. So here's kind of like what we saw earlier with that text plan, other than there's a top inside of here, but you pretty much read it right to left. Some people say that's not correct because it actually does take this top and send it to the cluster index scan, because if we hover over it, we see a little more of the information, and one of them is it's just pulling those 100 rows out. So the estimate on that part is that it's just going to find those 100 rows because the top was slid to that particular point. But to easily read it, and the reason I see that is because you got these little arrows. So those arrows must mean something. So we're going from right to left as we read this execution plan. Same kind of clustered index scan. There was a clustered index on this table. Our 2 compute scalars, the top, which is 100, and eventually we had the select. And if you notice, there's a little exclamation point there. And this is nice because it tells you what's the warning of this particular plan. So it does some kind of syntax evaluation or sort of thing, and saying this may affect your cardinality estimate in your query plan choice. And if you knew the execution plans, you probably have no clue what that means, and that's okay. The thing I'm looking at right here is this estimated subtree cost. So subtree cost of this query is 0.005. I'm not going to go into what that number means. It's held back from some previous version, and someone else might talk about that in another talk, but it's just kind of a measure on what this thing, quote, costs to run. All right, so that's displaying of the plan. So we didn't have to run that to look at it, but now I'm actually right click and add the include actual execution plan. And then when we run it, we get the results in one tab, this results tab, which everybody's probably familiar with. And then we get this other little tab here, execution plan. So we can go there, zoom to fit. It's pretty much the same thing that we saw with the display estimate. It could be an estimated plan is different than the actual plan. Did I turn on? No, okay. Let's look at 2 side by side, the top 100 and then one without the top 100. And you can pretty much see that the cost over here in the select 0.05 for that one and 0.55. So that top does make a huge difference on the cost of the plan, even though really it's still doing a clustered index scan on each one of these. So it's only returning the rows. How do we know how much is returned? If we hover over the line, we'll see an actual number of rows and even an estimate number of rows. They even give you some size information if you're so curious. Another important part here is if you look at each one of these, that they kind of tell you where the cost is, 0, 0, 0, 0, 0, and 99. So I mean, if you're performance tuning, you want to get to that point there to figure out what to do better. Well, obvious, I probably shouldn't have a select star in my select statement if I'm a good DBA. So I'm going to turn on something else called Statistics IO on, and I'm going to look at those two queries again. And in messages, I actually get a little more information. I believe you can get this in the execution plan as well. I like looking at it here. You can see here that there are 7 logical reads. So that select top 100 has 7 logical reads. So they're reading 7 data pages out of memory, which is logical means, and displaying that to your client. You see the physical reads and the read aheads have 0. That means everything satisfies queries in memory. Well, it's in memory because we've been running it about 5 times. You'll also notice on the second one, without the top 100, we have a logical reads of 889. So because there's not a top 100, it's reading more data, needs more data to be returned to the client. There's actually another one called set statistics time on, so you can see compile time versus actual work at that particular step. I'm gonna free some caches, so I don't have anything, run that again, and lo and behold, there's a change. We now have read ahead. So even though it needs 7 logical data pages to satisfy this query, physically from this query, it really only said to read 3, but the intelligence of SQL Server says, I'm gonna go ahead and read ahead and get a bunch of other things in memory just in case you need it later on. And that's how the intelligence of the query caching or the data caching in SQL Server kind of works. It kind of reads ahead because it's probably reading in these what's called 8K data page extents. One extent is 8 of these, and it's reading more than what's needed. Now, if I clean it again and run that top and then run the second one, the first one has that same information about the read aheads, but the second one does not. It just shows those logical reads and there's no physical reads or read ahead. Because the first one satisfied what needed to be in cache to affect the second one. So that's kind of a quick history and look at the different types of execution plans, statistics that were kind of the working area of looking at performance data inside of SQL Server. We're going to return to the slides and talk about some terminology. Query plan is what we saw. It's used by the optimizer. I still reference this. It was 4 articles Gail Shaw wrote like a decade ago, maybe sooner. She does a great job. There's a guy on the call, Hugo, who has a whole site on execution plans that you should go see. He probably has some good articles as well on it. But I thought those were always good articles to go back and reference about the optimizer, how the optimizer works. So we have the display of the estimate. We had the actual. Now you actually can look at live query stats. We'll see an example later. I used to say there's 3 scans, but there's 3 basic ones you might see today: heap, clustered, and non-clustered. You can actually have a column store scans as well now. So I guess there might be 5 you can have, and it could be more than that I don't know about because I haven't experienced them yet. But there's 3 basics: a heap, which means you have no clustered index; clustered index scan, which means you have the clustered index on the table; or a non-clustered index scan, which means it's scanning an index to satisfy the query. You also might see a seek as one of the types of data extraction methods. And it's supposed to be a good use of an index. Say supposed to, because majority of the time you have a well-designed database and it's seeks are good. After the seek, you might see what's called a lookup. And this lookup seeks more data to be extracted to satisfy the query. You can see a key lookup and an RID lookup. Key means there is a clustered index. RID means it's a heap with no clustered index. And I'll have demos of both of those. So let's go look at the seeks, scan, seeks, and more. I'm gonna go ahead and get in the right database, drop in the indexes that I might not want in here. And I am going to display the execution plan of this query. The query is pretty basic. it's taking the table database log and it's saying select all the columns. It's not using an asterisk, but it's actually showing all. And we get a table scan. If we hover over the select, we can see the cost is 0.443573. So we'll just keep that in memory. It's 0.44 something. So it's there's no clustered index, so I get a table scan. So, in my logical mind, it seems if I were to put a where clause, then I would get a better plan. So I might include my actual plan, bring this up a little, go to the execution, and lo and behold, it's still a table scan. There's no indexes on this table. So it can't do anything to improve it. Even though it's returning less data, it still has to do the same scan. And in execution, it's got to scan all those data pages to try to satisfy the query. So let's make our first, what I think should be the first obvious key to a table or index. It would be your primary key. We're going to create a primary key, and it's going to be clustered. So this is going to be our clustered index on database log ID. Let's go to that same query. And all we've done is moved it from a table scan to a clustered index scan. And lo and behold, the cost is still 0.44. So really, even by adding this primary key clustered index, it just organized the table into a clustered index, but hasn't really done anything to improve the performance. It's because we're selecting the same stuff. So let's go ahead and add that where sys, database user sys, and we get the same thing. So this index, the primary key, still can't really make it any better performance because it still has to scan the whole table to find a database user to apply the filter to it. All right, so we're going to continue on here and add now a non-clustered index. We're going to add it on 3 columns, database user, schema, and object. And now when we do the select star from the table name where the database user is sys, and then our cluster database user is the first column. So it should satisfy this. If I look at the execution path, lo and behold, we get something new. We have a better cost, 0.004 now, and we have a seek, a nested loop, and then a key lookup. So now we split it from table scan to clustered index scan to now a seek, loop, and a key lookup. If we hover over the lines, we'll see that there's actually 15 rows returned here. And then those same 15 rows have to go to the primary key to get the rest of the data. So our index seek, if we look at the bottom over here in the properties of it, we'll see the output list as those 3 columns plus the primary key, which is the clustered in our output list. And it shows the object it used, that non-clustered index we created. And then it also shows a seek predicate, which if you see the seek predicate, that's a good use of the index. If you see predicates, which would be above the object, it means that it couldn't use the filtering in the index, but it still had to do a predicate on the top of the seek. So a good, nice query now that it's used some additional columns. We'll launch 2 of them side by side. One of them has the DBO as the database user, the other has the sys. This one has 1,596 rows, and this one has 15 rows. Our cost is 0.01 for this one, 0.01 for this one, and our cost is 0.003 for this one. So by having that index, even though they're both doing an index seek, they're seeking to that point in the tree where it finds the start of DBO or sys and reads across till it gets to the end of that value and returns that data. So now we're seeing good uses of an index. I'll do this just to show you the count, 15 versus 1596. And then I'm going to show this one. This is a like statement. One of them has the wildcard at the beginning of the text value. The one of them has it at the end. And you'll see there's a big difference here. The one with the wildcard at the beginning does a scan, index scan, whereas the one with that at the end does a seek. So by putting it at the beginning, it can't really use the index to find anything. It's having to look at the end of the column to find it. Whereas that we placed it at the beginning, it's able to use that particular index. And there's a big cost difference, 0.016 to 0.003. So that's just a look at using the like operator. If I go do a select on those 3 columns, you'll see that in the execution plan, it's using that clustered index. You'll see if I hover, I'm hovering over this and it's giving me a printout, a view pop-up of all the properties I might want to look at. But you can always go to the side here and look at the properties and see everything. So as I click on an iterator, I'll see values over here for it. At least I should. Let me see, right click, property, there you go. And you can actually see the statistics here. You can see the number of rows, how many threads it used, the defined values. And I believe at the end, you still get that output list that shows each column that was extracted from this particular iterator. So you do have properties. You don't have to just hover. Sometimes you hover and then you move your mouse, it goes away. Well, if you just go right click, go to properties, it'll stay fixed there and you can look through those values. Now, what I'm going to do here is I am going to, just to show a feature here, our output list of those 3 columns based on DBO. But if I go put the ID, so I'm adding the database log ID here, I execute that and look at the execution plan, I still have the same seek as that was used previous. And in addition to the 3 columns, that database ID is in the output right here. So when you create a clustered index, create the primary key clustered index, every non-clustered index created after that or before it will always contain the column or columns from the clustered index. It uses that to do the lookup, but it also satisfies a query so we don't have to go back to the cluster to find anything because the cluster value is in that non-clustered index. It might sound kind of confusing, but just something to remember. It's good to remember that, especially if you're trying to create better indexes for your system. Your clustered index probably should be as small as you can, like as little columns as you can. That's why you see a lot of people favor a identity column as like a primary key of every table. But you got a table and there's a business key that's unique, then you might want to make sure you have a unique index on that column or columns. So by making this as small as possible, when the clustered column or columns is copied to the non-clustered, it's less and less data that goes into each index. Every index that you create is going to take up more and more space. Now, I didn't use this in there, but there's a page compression now. They can say page underscore compression equals, data underscore compression equals page or row, and it actually shrinks the size of some of these. But don't use that to create many, many columns in your clustered index. So let me clean everything out here, go to my DBO, and let me try to figure out why I'm doing this one. Oh, I did a scan. Let me try sys. Sometimes this works, sometimes it doesn't. Yeah, there we go. All right, so I use database user sys. I have this index seek. I'm just having to do this key lookup. So if you ever hear someone talk about a covering index, that's what we have right here. So I'm going to create my non-cluster, give it a name on the table with a column, database user. And then I have this include statement. So the include will take those columns and I'll add it to the data page, but not the tree that you have to traverse to get to the particular data. So this is what's called a covering index. Before the include clause, you actually included those in the index, which made this thing the tree very, very fat. So it's a wonderful addition that SQL Server did there. And now if I do that query, is it on DB or sys? Change that to sys. You'll see that instead of having a seek with a lookup, we just have a seek. If I hover over that, you'll see all the output in the list. and we just had that seek predicate, which is good. That's a good way to have an index. So that's scans. That was table scans, clustered index scans, non-clustered index scans, as well as some seeks. All right, I'm gonna flip back to the slides and talk about some more terminology. So the next one is loop. There's a nested loop, which if you hover over it, it's gonna say this, there's each row of the outer joins with each row of the inner. So if you just hover over this in your execution plan, it does a great way of describing what a nested loop is. And you kind of see it. There's an arrow going on in the outer, and there's an arrow on the inner. That gives you a nice little icon for that. You can see the index does it too. It kind of shows you traversing the tree to find something, and then this little arrow to show the lookup. The next one is a merge. I heard this best described by someone in the session. It's like a zipper. The two data sets are in the same order, and it's just zipping the data together. Out and inner rows are sorted. It could be that you have a sort iterator to do it. Sometimes both the indexes is used in the same order, and it just zips the data together. Hash is a little more complicated. It's not bad, but it is the most expensive. And when things get large, hashing is the best. It puts this data, I wish I could describe this in details, but I just can't. It puts in these 4 buckets, hashes those particular keys, and then searches in the hash. There's a guy, AMI 11, I think he's somewhere overseas from North America, and he did a great session one time on that. I think he has LinkedIn articles or videos that might show his description of hashing, and it's really, really good. So let's go to the demos of the different loops. So we looked at scans and seeks, we did lookups, and now we're going to show the actual loops. I'm just setting my stuff up. And before I actually run this query, I'm going to explain it to you. Finally, right, Thomas? You're explaining it to us. I am selecting from the customer table, I'm interjoining sales order header by the customer ID. I'm just grabbing 2 columns, the customer's ID, sales order number, and I have a where clause on one particular customer. So if I run this, or the execution plan, you'll see it's doing a clustered index scan on that one row for that customer. It's going to take that one row outer loop. In the inner loop, it's going to go grab whatever meets that condition of that one customer. It could be one, more than one customer return. And we would do the first one, loop through the rows from the lookup, throw them to the select, look at the next value of the customer, do the loop, nested loop, we'll look at the data from sales header, and then return it. So very basic query. I'm going to add a little more to it. I'm going to add some actual columns that might be used for reporting, the account number, the order date, and the revision number, all from the sales order header. And what we'll see is 2 nested loops. So you can have as many of these as you want, or as the query plan wants. So it's the same 7 in the same customer ID, one row. In the first loop, it's going to try to grab those 28 rows. But what it sees now is it's got to do a seek by that customer ID. It's going to go through another nested loop. And then, the seek at the customer ID, the sales order header. And then it's going to have to loop through that and go grab the 28 rows from the clustered index now. And it's going to need more output. It needs that account number, that revision number, and that order date. So in the previous example, I was just looking at the 2 IDs. So it didn't have to really grab any, reportable data that was in the clustered index. It just looked at indexes that were created on the IDs of the table, the primary key or foreign key of the table. So here we actually have 2 loops, and they loop up together to that select. Now, if I wanted, I could create a covering index. You see creating a non-clustered index on customer ID, and then adding in the include clause, those 3 values. We'll run that query again. And I got rid of one of the loops. So now that index, and it's still a C because it's still on customer ID, but now I've got additional columns in the include. Someone might be asking too, now you got 2 indexes on customer ID. That's right, you probably shouldn't have 2 indexes on customer ID. You should probably delete the other one if it's not a covered index like this, and just use this one, and it'll satisfy queries that use both. It's not exactly an indexing course, but or session, but we'll talk a little bit about it. So here, now we're going to look at a merge. So basically, it is taking the product table, product inventory, joining on the ID, doing a group by the name. It's actually grouping by product name and summing the quantity. We run that, and we get a little more than just a merge. So the merge is happening because this clustered index is on the product ID to start with. It does have location ID. And then this inside of product inventory is based on product ID as well. So it's returning these 2 data sets in the same order. But lo and behold, look at this, the aggregate, which is only costing 3%, is within inside of the merge join. So it's actually able to do the aggregation of the inventory, the sum of the quantity, before it streams it back to the merge, which is the 432 rows merged with the 504. And that gives us these results of the sum of the quantity. Now, if we add something like location ID to the query and to the group by, it's actually going to move the merge join closer to the 2 tables, and it's going to do something called a sort. And if you notice, it is 47% of the cost. So before it can do this aggregate, which is what some might call a locking type of, is it a locking? I don't think the surrogate stream aggregate is, because it's sorting the data so it can sort, then aggregate and continue the flow to the select statement. But we've got a sort here, which costs something. The reason that's a sort is now the group I has the product name and that inventory ID. So those aren't 2 parts of the indexes before it actually does the merge. So we saw a little more here than just the merge join. Last, I'm going to do a complicated query. I'm joining the human resources employee with business entity address, and then to address. This is a very normalized transactional database, and also the person in order to get a job title, city, and the concatenation of the last and first name of the employee. And what this has, it does have some nested loops in here, but we'll notice right in the middle is a hash match. So this particular join of these 290 rows with this 19,614 rows, the best the query optimizer says is when I hash those 2 together and bring them further along in the execution of this. And it's taking the employee information and the address is at the business entity address, and then matching it or joining it with the actual address so we can get that city, the city, just the city inside this particular query. But that's a hash, and you'll know, the cost is 21. If you remember, 290 rows with 19,000 rows. We say, well, why isn't a nested and nested like that? Well, there's only 290, and then even though the output is 290, we just added the city to that particular join. It's only joined to 290 more rows from this particular business entity for the person. Yes.
There's a question in here too, which is how do we know that it's 4 buckets, or how do we know how many buckets we get on that hash join that SQL Server is going to divide stuff up into.
Yeah, I don't know the answer to that. I think it's something internal to the optimizer, the engine itself. That's how it does it. We'll look at well, we don't see buckets there. We'll look at a parallel processing where we can actually see the threads that are running. But this is all internal. I don't think there's anything you can see in the execution plan of what the 4 buckets are. It's all an internal hashing mechanism. Sorry.
That's okay. Thanks.
You're welcome. Oh, so Hugo is saying it might be much more. If Hugo's saying that, it's probably correct. So maybe back when I watched that session with Amy back in, I don't know, 5, 6 years ago, maybe the engine just had 4 buckets, or maybe he was trying to simplify the explanation because what he used was like the 3 or 4 different types of playing cards, spades, clubs, hearts, and diamonds. So maybe that was just an explanation that sounded good to explain the hashing mechanism. But if you might be right, Hugo, it might be more than 4, and I probably should take that out of this presentation. So sorry about that. I'm just trying to use an example that someone gave me at one point. But I can look into it. All right, so that's our hash. I thought this was interesting. I'm doing a join to product and the sales order detail, looking at product ID, sales order, and the order quantity. I'll look at the execution of this. I'll see a nested loop for just that one particular product, which has 4,600 lookups to the sales order detail. But if I go add a where clause with 2 numbers, the cardinality of that second one I'm adding actually brings me to a hash. So even though there's 2 products, the result from the 2 products are 18,000 rows. So because of the volume, it's going back, or it's changing it from a nested loop to a hash to find this. Even if I were to do like the and or, I get the same sort of execution plan with the hash. But if I take 2 rows or 2 products that don't have as many rows, it'll go back to a nested loop or the C. So the engine, sometimes I think I'm smart, but I think this engine is much smarter than us or the collective of all the developers, and it figures out the best plan for it. But if you notice here, and you'll see this in different execution plans, you'll see it says 2 of 2. So the estimate was 2 and the actual was 2. But if you look at the loop, it says 67 of 152. So it estimated 152 and it was actually only 67. So based on the statistics behind these indexes, it's trying to estimate how many rows are coming back, but in actuality, it's less than what it found. And sometimes it could be more than what it estimated. And that's another thing you read into these plans is how much or how accurate it was this estimated versus actual. All right, so that's the smaller subset. That should be it for that demo. All right, so we saw compute scalars, kind of like the concatenation of last and first name. We saw some sorting. It's either used by order by, distinct, or group by. You'll see that iterator come out. Aggregate is when you use the group by and have some sort of count, sum, or other Windows type function inside of your select statement. We saw the properties for more information, but what we didn't see was any of the inserts or updates or even deletes. And that's a good question. And the arguments behind how many indexes you should have or how many you shouldn't have really all depends on is this system transactional? Is it a data warehouse for reporting? If I'm having to report all my transactional, maybe I should replicate that stuff to another database and add additional indexes there so it doesn't affect the performance of your transactional systems. It's all a measure of tolerance by your company on how slow inserts or updates are doing versus how fast you need to get the reports back out. But I'm going to show you 2 things here. Before we get to the insert update, I will show simple sort. So here's just a select query on a product inventory, order by shelf. So here, because I ordered by shelf, I get that iterator that's 76% of my cost. This is only 24, 100% accurate, but the sort, you try to avoid that as much as you can in selects, because even if you were to create an index just on shelf to satisfy an order by, it might be one report in 100 that actually use it. But just know that that's usually the largest cost of a query. And we did this one earlier. This is when the stream aggregate was used for the query. So let's go to the insert update. I'm gonna clear everything. And I'm gonna do an insert. So there's nothing on this table. Doing an insert, I look at my execution plan, some constant scan, compute scalar, and it just does a table insert here. So there's nothing that it has to update other than the table itself. Cost here is 0.01. And now I'm gonna go back to what this table actually is. I'm gonna add primary key along with 3 non-clustered indexes. We'll do that same sort of select. And my cost went out from 0.01 to 0.04. So it's 4 times slower, but the cost still is very, 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 very minimal, 0.01 to 0.04. But it does increase your cost in here. And you see that it just really shows you the clustered index insert, which actually does the updating of the other non-clustered indexes as well. That's how it does it all within that one iterator. Now, let's look, and I'm a good DBA. I'm gonna do a begin transaction before an update. One reason I'm doing that is because I made this mistake before and it affected a demo afterwards. I couldn't figure out why everything was DBO, but I'm gonna do an update statement on this table. I'm gonna update everything to DBO that was assist. If I look at the execution plan, you'll see in the beginning, it uses an index C. So in this case, because the where clause is on database users, the index actually helps the updates. Instead of having to do a full scan, it's able to seek and then just update what needs to be updated based on that database user ID. And the cost, I think, is 0.07. Yeah, so it does cost something, but in reality, this is helping the update. So in some cases, it can help the update. We'll roll this back, just to make sure, and go back to our slides. All right, so this is really neat. Parallelism, cost above threshold, cost threshold for parallelism. SQL Server could use multiple processors. They might reference them as threads. In the server properties, the instance properties, you have a max DOM configuration. By default, it's set to 0. And the cost threshold, I think still today is set to 5. I might be wrong there. It might have changed in newer versions. But basically, these are 2 things that control or help adjust parallelism running in your database. You reduce the cost threshold to get more parallelism. You have 34 processors and it looks like only 2 ever being used. Increase to get less. It seems like everything's running a bunch. You need to kind of scale it back down so everything's not running parallel using many processors at the same time. New in 2017, you can actually set this on the database level. What I've noticed as a guide to some people who have database level type stuff have cross database joins. And so the connection that you're in, so if I was in master and I was doing from database name dot schema dot table join database name dot schema dot table, it's actually using what was set at the database level and not necessarily in the database I'm actually querying. So whatever database your context is for your connection is where it uses the level. Otherwise, it's using the server level. Just something to be aware of. It got me one time where I couldn't figure out why someone's query wasn't using the database level. It was all because they're running out of master with database aliases rather than being in the database and running at the database context level. Another new one, adaptive joins, which is something to help. It sees that it could possibly have multiple paths. You see two examples here where it's doing a index scan and a clustered index scan and an index scan versus just a clustered index C. Two possible paths. There's multiple paths that this adaptive join could use. It selects the best statistics, helps with parameter sniffing. So if you're seeing parameter sniffing, upgrading to a new version of SQL Server sometimes handles it for you. And we're going to see an example of that as well in this demo. So let's go to the next demo. What I'm talking about parallelism, if I right click on my instance and go to properties and advanced, I can see that information here. So it's a cost of threshold and my maximum degree of parallelism. So I'm going to go back to my query, make sure my advanced options are on. I'm going to go to this 2016 database, set the parallel cost of threshold to 5, degree of parallelism to 2, free up caches. I'm going to run this query. I'm sure a lot of y'all write CTEs nowadays, common table expressions. Really nice and handy functions are T-SQL to use, not a function. But I'm gonna run this particular query. It's doing some inner joins on sales order header, sales territory, country region. It's doing a rank over total amount to get a particular output by country name, customer, total amount, and its rank. Now in the execution plan of this, one thing we see here too, which I hadn't really talked about, is there's the missing index feature. You can see it's suggesting an index that might impact this by 15.18%. Probably I wouldn't add this index to help this. But if you notice, right in the middle here, we've got a series of iterators that run parallel. There's two little arrows on each of these three iterators. Now, if I click on one of those, sort, expand my properties, over here in the actual number of rows, you'll see thread 0, which is the head thread, and then two other ones that have distributed half of the records, about half of the records, to two different threads so it could process and then bring the data back together. So this is how it helped this query to run faster. So we look at the cost, it's 4.6. Now I'm going to do something here. I'm going to use a query hint of some sort. I'm going to say max dot is 1. So I'm going to force this to just run without parallelism, just with one thread. And you can see that those parallelism went away. And if I hover over the select, you see the cost is 6.5. So 6.5 is above 5. If I don't do the max dot 1, it'll look and say, let's run in parallel. Go down from 6.5 to 4 point something by running in parallel. Now watch if I change the parallelism to 4. So instead of 2, 4. Run that same query without the max dot. It's running in parallel. Here's my parallelism. If I hover over select, it's now going down to 2.9. So from 0 to 2, it went from like 6.5 to 4 point something, maybe a 33% decrease. From 2 to 4, it went to 2.9. Now, if I keep going up and up, eventually it'll level off where the number of processors or threads doesn't really help the query. But let's do one more thing before we jump out of this. And I'm going to set the cost threshold to 7 here. Go run that query again. And you'll notice there is no parallelism. The cost is back at 6.5. So 7 is greater than 6.5, so it doesn't try to run parallel. I just wanted to show you this as a example of how that cost threshold works and the max stop and how that works. Now, watch this. I'm gonna change, I'm gonna change the databases from a 16 version to 17. And really all that is if I go to the properties, options or file, oh, it's options. Here is the compatibility level, 2016 versus 2017. So I changed it. I'm gonna run this query. All those parallelism things are for the 2016 database. I'm gonna run this, and just from upgrading this database from 2016 to 2017, my cost went down to 1.17. So what did SQL Server do? An adaptive join. So now the intelligence of the query engine knows to optimize this even further and give you better performance. So the exact same database and a different compatibility level went from 6.5 to 1.1. Huge increase from 2016 to 2017. I haven't tried on 2019 database yet, but there might be even more improvements in the performance of this. So that's parallelism. Adaptive query, we just saw the adaptive query. It's the same query. Oh, and one more is the live query statistics. So watch this guy here. So I'm in 2017. I've got this join union that's being done in my data warehouse and my analysis services cube. I'm a select include live query statistics. Okay, so watch this. You gotta be real quick because it's gonna happen really fast. I'm gonna try to draw, see the little dotted lines. It happens really, really quick. So the live query statistic shows that this part is finished, but this part is still running. Okay, so it happens real quick, so you really can't see it in that query. But why would you want that? Watch this. I wonder if someone did a select on the wrong columns. And they said, well, this thing's been running for 10 hours. Well, you can see where it got. It did the 2 index scans, finished. Those 2 lines are bold, but it's still cranking here. You know, another thing the live query statistics give you is you got some different things on the iterator. For instance, it shows the seconds, and then it gives you a count of the actual rows versus estimated rows, and it kind of just keeps cranking along. So you kind of see those numbers as they go along. You can see this one got to 30,480, but this one's still on 76. So the live query statistics can let you see how it's running. There's some ways to look at this while something's running, but I'm actually executing the query itself. So that's in addition to, I'm gonna stop it. So we had display, estimate, include actual, and now include live query statistics. So more and more things SQL Server is adding to the mix. So that's the adaptive joins, parallelism, which I think is really cool to be able to understand that, and live query statistics. So to top this all off, there's something called the query store. So these plans now can be stored in your database. It has to be turned on. If you're in Azure, it's turned on automatically. Originally there was 4 reports. They added 2 more. I think there's 7 now in here, but just unbelievable wealth of information now is inside of your database itself. So let's look at the query store, and this will be our last one. I'm running some queries just to add some more information to that query store. But if you look over here in my database, there's a section called query store. It's only on if you turn it on. So the query store right here in the properties, and you can see the settings. There's ways to purge the data, but it's always cumulative. There's ways to take the flush interval, collection statistic interval. If you ever see it in read-only mode, it means usually it's full. If databases come as off, I don't even think you could change it in the model database. I'm not sure, but there's a bunch of storage mechanisms here. It's really different for a transactional versus a data warehouse type database. Now this is capturing my information, and now I have these reports to look at. So instead of querying DMVs and DMFs and trying to put everything together, you can just say, okay, I want to see regressed queries. Oh, look, based on duration or total, number 54 seems to be the worst. I hover over it, gives me the query, and click on it, and it actually shows me the different plans. I can click on one of these plans, shift click on another, and over here is a compare plans. Now I got both of the plans side by side from this particular query. Now it's highlighting things, it sees it's different. You look to the right, it's actually putting two different panes together and showing you these not equals, so you can better determine what change, what is the query plane change, why is that different? I'm going to tell you what's different. I did this on purpose, is really, let me zoom back out. So that didn't work very well. It's telling you that this cost here is significantly less than this cost. So it's trying to point you to that. But really what happened is I went from a clustered index scan to a column store. So I added a column store index, which made that query run a whole lot better. I think it runs better. Let's see, the cost is 4.6 here and 2.1 there. Yeah. So it's about twice as it runs about twice as good when you're using a column store index over just a clustered index. So that was the showing of the plans. I could, if I wanted to, I could say, is that column store? Yeah. So this is the non-column store index. I could highlight that particular plan and go up here and say force that plan. So now I can force that plan on that query. So anytime that query runs, let me see if I can find it. Here it is. If I try to run this query, I didn't do this. Using the cluster. Okay. If I take that off, there's actually a display of the force plans, and I should be able to remove it. Unforced plan. Go back to the query, run it again. Now it's using, oh, well, maybe the non-clustered or the column store is not on there. Let me add it back. Yep. That was a bad example. It's okay. It's using the column store now. And if I go back to force it, now it's using the cluster, not the column store. So I can force a plan if I want. It's dangerous, but you can do it if you want. And you got a display, you have a report to show you that information. High variations. This is a really popular one. Wait state, so I can see parallelism and network IO is the biggest ones. Everything can be changed here. It's based on total wait time, but if I wanted it on average wait time, I could do that. Any of these reports, like overall consumption, you'll see a config where you can actually select the columns for the chart, the interval that you wanted, and some of them have, once you display some information here, have a, that's the query, you can jump to the query, but some of them have a table, here it is. So instead of seeing a graph here, I can see the tables of the queries, and then I can see the columns that are being used in the particular graph. Track queries, I can go to this, type that 54 I saw earlier, and go straight to it, see it over time, be able to see that it's been forced, still unforce it, or one. And I can click on the two to show them. So that's the query plan. Unbelievable tool to help you with the execution plan. So now you, not necessarily, your system's running, and now instead of having to execute a query again or display estimated, you could go into this query store and retrieve queries that have been running in the past, see their selects, see what indexes they're using, and look at the query plans that's been stored without actually having to run these. That was the last demo. Thanks. My name's Thomas LeBlanc, Smiling DBA. My website's thomas-leblanc.com. And you can email me to smilingdba@gmail.com. And that's it.
Woo! Yay, thank you so much, Thomas. Thank
You're
you.
welcome.
Josh, you still there? Have you left us? Are you
I have
gone?
not.
Oh, hi. I had to duck out for a couple minutes there, so I'm glad that you were able to catch that. I'll catch the middle bit in the recording. Thank you. Thank you, everybody, for coming. Thank you.
Is there any other questions? It doesn't look like it.
I know.
Nothing else showed up in the chat other than
I'll
the
have to
one.
get with Hugo and talk to him about the 4 buckets. That might be something I need to change in my demonstration. Execution plans are good. If you're a DBA or a developer, I did this at a local SQL Server .NET user group about 3 months ago. We started that back in person, and developers are always interested, even if they're not even using SQL Server, because one of them was using PostgreSQL. The other one was using MySQL, and they have very similar information that they get from their queries. So it's always a good thing to learn how these execution plans work.
That's good stuff. Thank you.
Yeah, thank you so much for coming and for sharing that with us. Really appreciate it.
Not a problem. All the thank yous that people are saying. Where will this be posted? We need to refer back to this on YouTube. Okay.
I just put the
I'll
link.
place everything on YouTube.
Yeah, I just put the link to the GroupBy channel on YouTube.
Go back through it and find some old ones to watch. Is that it?